Hello everyone, this is Yinlin Ji from Geoenergy section of GFG, German Research Center for Geosciences, Germany. Today we're going to learn the basic principle of effective stress, which was first introduced to deal with the interaction between total stress and pore pressure in a porous medium. It is so important that it's commonly seen as the cornerstone of rock and soil mechanics as well as hydrology and subsurface fluid flow, because fluid really matters in subsurface activities. In this lecture, I'm going to first introduce you why fluid matters in subsurface activities, followed by clearly defined learning outcomes. Then I'll introduce you Tazaki effective stress and the effective stress coefficient, followed by typical applications in geoenergy systems. Lastly, I'll summarize the take-home messages. Here in this little bit complex figure, it shows us that we have various ways of utilizing the subsurface for sustainability and decarbonization. I'm going to assume that you have the basic knowledge about contemporary sustainable subsurface use, basically including geoenergy extraction and storage. Here I'm going to summarize the different types of fluid that may get involved in contemporary subsurface activities, including different types of hydrogen, water at different temperatures, compressed air, as well as CO2. Just for information, there are different types of hydrogen which are classified based on what kind of fuel it takes to produce it and whether or not carbon is captured. But in any case, this figure shows us that fluid really matters, especially in contemporary subsurface activities. So it's important for us to understand the basic principle of effective stress in order to better deal with the interaction between total stress and the pore pressure in the subsurface. Here I list the learning outcomes of this lecture. You're going to bear this in mind when we're going through the content, and you are expected to acquire these outcomes after the lecture. First, you are expected to understand the principle and derivation of Tazaki effective stress while recognizing the assumptions and the applicability of Tazaki effective stress. Then you should be able to describe the definition, development, and the general form of effective stress coefficient. You are expected to be able to use the effective stress principle to explain the underlying mechanisms of hydraulic stimulation and fluid-induced seismicity. Before we go into the excruciating details of Tazaki effective stress, we certainly can't get around the undisputed father of soil mechanics, Carl von Tazaki. He first proposed the principle of effective stress in 1923 in German language because he is Austrian. And the first English version of this principle was published in a conference paper by Tazaki in 1936, in which he was dealing with the shear resistance of saturated soils and the angle between the plane of shear. In the very beginning of this paper, Tazaki stated that the stress in any point of a section through a mass of earth or soil can be computed from the total principal stresses sigma sub 1, 2, and 3, which act in this point. That's the definition of the total principal stress. If the voids of the soil are filled with water under stress P, that means a fully saturated condition. The total principal stresses consist of two parts. One part P act in the water and in the solid in every direction with equal intensity is called the neutral stress, or as more commonly addressed as the pore water pressure nowadays. The balance sigma sub 1 prime, 2 prime, and 3 prime represents an excess over the neutral stress, or the pore water pressure P. And it has its seat exclusively in the solid phase of the earth or soil. This fraction, that means the latter fraction, the balance of the total principal stresses, will be called effective principal stresses, which takes the simple form as below. Sigma prime equals sigma minus P. And particularly, let's take a look at this last sentence. It has its seat exclusively in the solid phase of the Earth or soil. We're going to revisit the sentence after the derivation in the next slide. Although at its first proposal, Tazaki effective stress is empirical, it could also be derived theoretically based on certain assumptions. Here in fully saturated geomaterials, like rock or soil, their grains packed together, fully saturated with fluid, under quasi-static conditions. Both grains and fluid constituents are assumed incompressible, and the grain particles are with point contact. Then at this contact point, there is a contact force P sub S, which can be resolved as to the horizontal and vertical direction. If we draw a near horizontal cross section passing through a series of contact points from 1 to I, then we have the equilibrium forces on AA because of the quasi-static conditions. This equilibrium is shown in equation 1, that is the total force is equal to total stress times total area, which is equal to the sum of vertical contact force and the force provided by the pore pressure, that is the pore pressure times the area on which the pore pressure is occurring. This area could be calculated from the total area and the contact ratio alpha sub c. Because of the point contact assumption, alpha sub c is almost 0. Then we substitute equation 2 to 1 and divide both sides by a, we have equation 3. And we're going to rearrange equation 3 and compare it with Tazaki effective stress as shown here. Then we have equation 4, that is, theoretically, if Tazaki effective stress is roughly the difference between total stress and the pore pressure, and is theoretically the ratio between the total contact force and the total area. So if we revisit this last sentence of Tazaki, which states that the effective stress has its seat exclusively in the solid phase of the earth or soil, that means we have a better understanding of the effective stress. The effective stress is really exclusively carried by the solid phase of earth or soil, but it's not the effective contact stress. Rather, it's the contact force divided by the total area. So it reminds us that it's better not to use this kind of denotion, because sigma prime normally stands for effective stress, and effective stress is not the contact stress. Rather, again, it's the contact force divided by the total area. Then we want to talk about the applicability of Tazaki effective stress and introduce the effective stress coefficient. The Tazaki effective stress has been shown to hold for soils for most practical purposes, while moderate to significant deviations have been measured for rocks. Then effective stress coefficient is thus proposed to deal with these deviations and scale the rock's susceptibility to pore pressure. That is, we put a scaling parameter before pore pressure, and this scaling parameter is referred to as effective stress coefficient, or Biot coefficient, or Biot-Willis coefficient. There are various expressions of the effective stress coefficient. At its first proposal, alpha is equal to 1. Later, it's correlated with porosity and the ratio of Bach modulus of grains and porous media. It could also be related to both of them. And particularly, we want to take a closer look at this equation. This equation is the effective stress coefficient specifically for volumetric deformation. It's an important parameter in polar elasticity. It has been first theoretically derived by Skepton in 1960 and then experimentally validated by Nur and Bailey in 1971. It tells us that The effective stress coefficient for volumetric deformation can be obtained by subtracting the ratio between the bulk modulus of porous media and constituent grains from unity. And this parameter decreases with higher effective stress, as shown in this figure, for various of rocks according to lab measurements. We can see this effective stress coefficient, alpha, decreases with higher Tazaki effective stress. This is primarily because of the increase of bulk modulus of the porous media, accompanying pore or crack closure at higher stresses, while K grain is assumed as a material constant. However, K grain can also vary with total stress, especially for clay minerals or organic matters, those soft material or soft constituents. Furthermore, for rocks with several constituent minerals and heterogeneous macrostructures, K grain is difficult to measure in the lab or to estimate using mixing laws. Then we need a general expression for effective stress coefficient for any physical quantity, not only for volumetric deformation, which should be easily used to estimate this coefficient from lab measurements. In 1972, Todd and Simons theoretically derived such an equation for effective stress coefficient for any physical quantity, for example, volumetric deformation, wave transmission, and permeability. According to this equation, the effective stress coefficient can be obtained by subtracting a ratio from 1. If we take a closer look, this numerator quantifies the susceptibility of quantity Q to the change of pore pressure, and the denominator quantifies the sensitivity of a physical quantity Q to the change of total stress. So this theoretically derived equation is also intuitive because it quantifies the relative contribution of pore pressure and total stress to the change of physical quantity Q. And particularly, for example, the effective stress coefficient for volumetric deformation can be written as below. We just need to replace this physical quantity Q by X sub V, which stands for volumetric deformation. Then, in the lab, as shown as an example in this figure, in the lab we just need to measure the volumetric deformation by systematically changing the pore pressure and the total stress. Then we quantify the slopes and substitute these slopes to this equation, and then we obtain the effective stress coefficient for volumetric deformation. And similarly, for any physical quantity, we can use this equation. We need to replace this Q with the quantity that we want to focus on. And then we measure this quantity by systematically changing the pore pressure and total stress and quantify the slopes, then substitute those slope values to this equation and derive the effective stress coefficient for the specific physical quantity Q. Then we may wonder, what's the relationship between the specific equation for effective stress coefficient for volumetric deformation, which we discussed in the last slide, as shown here, and the equation here? It's readily derived that this equation is just a special case of the general expression for effective stress coefficient for volumetric deformation. It's strictly applicable only when Tazaki effective stress is small. The detailed derivation is not shown here, but is attached in the last slide. Then we may want to talk about induced seismicity in geoenergy reservoirs. There are two main categories. One is injection-induced seismicity, the other is production-induced seismicity. Both of them are resulted from fracture or fault reactivation caused by injection or production. And in terms of injection-induced seismicity, it shares the similar physical mechanism with hydroshearing. But in addition, it may also be controlled by the frictional property of the fracture and its surroundings. But in any case, it can be readily explained by Tazaki effective stress. That is, the increased pore pressure tends to move the Moore circle close or cross this fracture or fault failure envelope, potentially resulting in injection-induced fault slip and seismicity. But when it comes to the production-induced seismicity, the production will reduce the pore pressure and move the Moore circle far away from the failure envelope, and there will be no earthquake. This is contrary to the observation in typical gas production fields, like in Groningen, the Netherlands. There are abundant induced seismic events with surface subsidence. So we need to incorporate other mechanisms. The mechanism is pore pressure and stress coupling, PSC. For example, in a normal faulting stress regime, the reduction of pore pressure will move the Moore circle towards the right-hand side. But it can also change the effective stress in different directions with different magnitudes. Then it tends to enlarge the Moore circle. So in this case, the enlargement of the Moore circle still results in the possibility of crossing the failure envelope and the earthquake. Here I show you the take-home messages. I'm not going to read it for you, but you can read it against the learning outcomes to examine whether you have acquired the learning outcomes after the lecture. References and reading materials for your consideration after the lecture if you want to dive into some of the details of the principle of effective stress. Then, as I said, I show you one slide to demonstrate the consistency between general expression and a special case of effective stress coefficient specifically for volumetric deformation. Then lastly, I would like to end up with this cover slide, and then please feel free to let me know if you have any queries. Thank you.